So, to introduce myself before we do get going, for everyone who has been to one of these workshops before or has followed us on social media for some time, welcome back. Super great to have you guys around again. And for those who are new or haven't watched a workshop before, welcome. We're Catalyst Chemistry, and my name's Jeff. I'm one of the tutors at Catalyst, and we essentially are a fully online program that gives students the fastest path to crushing chem, or HSC Chem specifically. We have achieved some pretty good results. Last year we got our first state rank, which was awesome. Tons of band 6s, some high range 99 ATARs, which is always great to see as well. Our students have some pretty good things to say about what we do. And the way we do it is we have the best tutors, we have the best resources, we have the structure that's set up in a way for you to actually go through this term and win with ease. And our classes are fully online, so you can do it from home, and they're in small groups. So if you're keen to get a 3 to 5 week head start for next term, and I'm thinking very far ahead, that's the way we teach. We teach so that you learn pretty much all the content in the holiday, and you walk in the classroom day one already confident with what is going to come out of your teacher's mouth. You know exactly what's going to happen, and you just are much more confident in classroom. That's like the main thing that you get out. By the time exams come around, you've done so many questions and had so much feedback that it is a near impossibility that you don't at least do better than if you didn't do all this extra stuff ahead. In fact, it is much more likely that you do very well. And our students find that because of that structure, it's a lot easier to go through the weeks of term rather than have to cram the night before or feel like at the start of the term you're already starting behind. So if you're interested, for next term, Module 7 obviously is what will be for most of you. We also do have a Mod 6 course if anyone's doing it out of order, but I don't imagine anyone here would. Mod 7 will start in the holidays, and if you're keen for that, the details are on our website. You can express interest to join through there. And the special offer that we're running for you guys at the moment is if you join right now, basically today, tomorrow, anytime before your exam this term, you get access to all of Catalyst's Term 1 resources, recordings, everything that you missed for free when you sign up for next term. So you may as well sign up for Term 2 if you want to get all this stuff for free. So all the notes on the screen today, all of our homework booklets, our exam, all of our marking outside of class support, that's all included for you. And if you sign up before March 29th, you also get a cheeky little discount for early bird enrollment. So if you are keen, click the link in our bio on Instagram or go through our website, submit a form, and we'll see you inside if you're keen. But that's enough about that. That's not why you guys are here. Let's talk all things Mod 6 today, and let's jump over to what actually matters, if I can click the right button. All right, so I presume by now most of you have gone through all of Mod 6 content. You're pretty on top of most of it. So the purpose of today is give you the Band 6 touch on back titration, on buffers, and on the main calculation types, just so it's all front of mind for your exam as you go in for the next few days / week. I'll start today with buffers, just because it comes earliest in the syllabus, and we'll work from there. So let's go from, we'll go from the notes. Okay, here we are. Cool. So these are the Catalyst notes. All the Catalyst students have access to this. They've been here, they've had them from 8 weeks ago, but you guys get a little sneak peek in if you haven't already joined us. Buffers first. Everyone in the chat, can you type your definition of what a buffer is to the best of your ability? What is a buffer to start us off? What is a buffer? What is it made of? What does it do? I'll give you all 30 seconds. Best attempt at typing something out. I know there's stuff on the screen, so I'm going to get rid of it now. What is a buffer? What would you say? Equimolar amounts of weak base and conjugate acid. Great. I'm liking this wording. Can we get someone to add on as well? What else would you add on? Tommy's saying you missed something. And quote, little bro. A A weak acid and its conjugate base that resists the change when acid and base are added. I like the extra detail. Good. pH resistor between acid and conjugate. I think you mean conjugate base, Jared. Buffer is a substance that contains equal parts of weak acid and its conjugate base that helps resist a change in pH. Good. Okay, we've got the main bits. As we've said, a buffer is a weak acid and its conjugate base. Can it be a weak base and its conjugate acid? If that makes sense. Can it be that? Yes or no? Can it be a weak base and its conjugate acid? Yes, absolutely you can. So it can be either way. You can have a weak acid and conjugate weak base, or you can have a weak base and conjugate weak acid. Either way, you can form a buffer. Then we've said that they resist pH changes. So that's a really important part. When you have this weak acid and weak base in solution, and you add either acid or base into it, the pH will not change significantly. But can we actually explain why that's the case? And that's what I want us to be able to do by the end of the day. That's the first learning point. Why is this actually true? Because I think this is very poorly understood. Then we mentioned something about equimolar. Being equimolar, having equal amounts of weak acid and weak base. Can you have a buffer exist where the weak acid and weak base concentrations are not exactly the same? So let's say, for example, you had acetate, and this is my favorite go-to. I just use it a lot, so excuse if it comes up a few times. Acetate and acetic acid. If you had 0.5 molar and 0.4 molar in solution, is that still a buffer? Like, can it still act as a buffer? What do we think? Will it still act to buffer the solution? Great. Callista Klep, shout out, that's perfect answer. Yes, you can. It is still a buffer. It's just not quite as effective at buffering both ways. So when we say equimolar acid and base forms a buffer, just be careful with what you mean. That would be the case where you have this, like, the most effective buffer in both the basic and acidic direction, but you can have a case where you have non-equimolar concentrations and there still is a buffer. So just be careful. So what I want to also address then is, what is it when we say a buffer has capacity? So buffer capacity, what is that and why do we care? And how does that relate to then how effective a buffer is? Okay, cool. And night, as you said, as long as it's comparable amounts, that's usually a better word that I prefer. I prefer saying a comparable concentration of weak acid and conjugate base is usually a nicer way to put it. So thank you for that. Great. So buffers. Definition is here. We have acidic buffers, we have basic buffers, depending on what pH they lie at when you have the buffer in existence. So when can you identify a buffer? There are sort of two main streams of what you can see with buffers. You can either have the case where you have two conjugates being added together in solution. So the common question stem is we add some acetate and we add some acetic acid into solution, and what do you now have? Or if we add acid into this, will it resist pH change? The answer is yes. So when you add the two conjugates together, you'll form the buffer. That's a common way you'll see it. The other case that's a bit more disguised and is more common in application is when you have a weak acid or weak base that gets partially neutralized. So in your titrations, where you have a weak acid or weak base being titrated, and for simplicity, I'm just going to say weak acid for now, and most times I mean both weak acid, weak base. But let's say you have a titration where you're neutralizing a weak acid of acetic acid. Acetic acid. And you start your titration down at a moderate pH, because it's a weak acid, so let's say pH 3. You initially have your quick neutralization of free H+, then you have a period where it's relatively flat for spiking up and then reaching a high pH, and let's say that we're adding in volume of NaOH in mils. Let's say this is 25 mils. Excuse the slightly chunky graph. This is 7, and our equivalence is around like a pH 9, let's just say. Cool. We can say that a buffer is established where we start to see resistance in pH change. And so essentially from this point onward, this is our buffer region where we start to see resistance in pH, because we are adding in OH minus. So we know the CH3COH dissociates into, let's do it the Bronson Larry way. Dissociates into CH3COO minus plus H3O plus AQ, L, AQ, AQ. And we're adding in OH minus, so the OH minus reacts with any free H2O plus to make H2O. Okay, and in doing so, that is taking H3O plus out of solution. All the free H3O plus gets reacted, and the point where it's all the free floating H plus gets reacted is this point here. Then you start to see buffering occur, and you would technically have buffering occurring through the whole process there, but you would have significant buffering which shifts this whole equilibrium to the right in order to replace any reacted H3O plus once the buffer is established. And so once you have this H3O plus that's been buffered, you make some acetate, you react some acetic acid and some H2O. Any further OH minus that's added in continues to react the H2O plus. So let's say again, you react some H2O plus, the system will act to resist that change, shifting right, bringing back H2O plus into solution, so that you pretty much end up where you started in terms of H2O plus. You once again make some more acetate, consume H2O, consume acetic acid. This whole region is a buffer, therefore, because until you exhaust all of the acetic acid, acidic change can be buffered. And once you exhaust it and you reach your equivalence, that is the point where you've hit buffer capacity. And you have no more ability to resist change in pH. Okay. So that was a whole lot of speaking. If you guys have questions at any point, it's not making sense, you want me to go back over something, explain it again, it means I've done my job badly, ask the question in chat and I'll explain it all over again. So we'll keep on going. Cool. So the first case we see it is titration in the buffer region. We can also see it in indicators. If you have a significant amount of indicator in titration, that can introduce error because an indicator is technically also a buffer. Because an indicator is a weak acid and a weak base in solution. Interesting. So that's why when we do our titrations, we only do 2 or 3 drops of indicator, not a whole lot, because otherwise the indicator can create inaccuracy through the buffer it provides. And the last part is in our real-world applications. We can see it in, for example, your blood buffer. You can see it in your intracellular buffer or your ocean buffer. You have those examples to learn as well. Okay, I'll go back over the equilibrium part and let's explain it through this diagram now, a different way. And another question, does that mean at the half equivalence point the buffer would work the best? Correct, because that's when you have half of your ion totally neutralized and you would have half of your buffer existing as CH3COO minus and half of it existing as CH3COOH in pretty much 50-50. So yes, no, that's correct. At half equivalence point, so right on here, half EQ, you have half acetate, half acetic acid, which means your buffer can have the most capacity in either direction. Most effective, therefore. Great point. Okay, let's explain the equilibrium shifting again through a new diagram. I find this is a bit easier for visualization. So now we have a, let's go down to this one. Same equilibrium. We have acetic acid which reacts with water to make H2O plus and CH3COO minus. 2 cases, you can either add hydronium or you can add hydroxide. Let's say at the starting point you have equal concentrations. So we're at that half equivalence we were just talking about. Equal concentrations of acetic acid and acetate. Let's take the case of adding hydronium in first. What happens when you add hydronium? If you add hydronium in, the added hydronium is the change to the system which your equilibrium will shift to resist in accordance with LCP, Le Chatelier's principle, which states that any disturbance of the system will be counteracted, will be partially counteracted. So which way should this shift? This should of course shift to minimize or decrease the H3O plus concentration. So to decrease H3O plus, we have to shift left in order to bring H3O plus back down, and it'll be near complete resistance, but not full resistance, because we can never fully counteract change. And in shifting left, we'll also be reacting off some of our acetate to form acetic acid molecule, which is now holding that hydrogen ion and not allowing it to be free in solution, or at least as much as it would have been before. And of course some water as well, but that doesn't really matter too much. So visually, what would have happened to our concentrations? We would have seen that acetate dropped in concentration, dropped in its concentration. Acetic acid rose in its concentration because we formed more of it to buffer the change. And what happened to pH? This is the question that I want us all to answer. Has pH changed significantly or not, based on what's happened to our hydronium? Has the pH changed a lot, or has it not really changed? Type in chat. What do we think? Has pH changed a lot or not? Great night. So pH would remain relatively the same, and we can visualize it because the H3O plus concentration has virtually negligible change after resistance. Negligible change after resistance. It's pretty much the same. It's slightly risen, ever so slightly, but in the grand scheme of things, the pH hasn't really shifted that much. And so if we were to show this on a titration curve, this would be a portion within the buffer region where it's pretty much flat. It's rising ever so slightly, but not really. And only when you start to get to lower concentrations of acetate and you start to run down the buffer, and in fact you start to exhaust it, that's the point where you start to see steeper increase. Kenneth asks, is the audio a bit soft? Everyone, is the audio soft or is it okay? I can turn it up if it's still soft. Just say louder or is fine. Adi says, yep. Does that mean soft? I think it means soft. I'll turn it up a bit. It's okay. I'll turn it up anyway. One moment. A bit louder. Yeah, let's do it. Okay. I think that's louder now. We're now in the yellow range. Should be better. Give me a reactor a thumbs up if that's okay. I'll assume it's okay for now. Okay. Cool. So what I want you to appreciate with the pH change is that it's a very, very small increase. And that's what we're trying to show with each of these buffer explanations. We're trying to show ultimately through the resistance and through the shifting in accordance with LCP, the change in hydronium concentration is very small, and therefore pH doesn't really change. And if we can do that, that's what our teachers want to see. Let's look at the other way, and I want you all to have a think about it in terms of now hydroxide. What happens if we add hydroxide to this buffer? Can it buffer that change, not just the hydronium one? We know the answer is going to be yes, but think about how. So let's look at the other side. If we add hydroxide. Okay. So the first thing that you should note, if you add hydroxide, what will react with the hydroxide? We can talk about it in terms of this equation, or we can talk about it in terms of this equation instead. CH3COOH plus OH minus. Cool. So for every buffer, there are 2 buffer equations. When you write your explanations, you should have both to be very comprehensive. But when you talk about the shift, you only reference one of the equations, if that makes sense. So we can talk about it in terms of either of the equations. Let's try the first one will be pretty much the same as what we just did. So let's do equation 1 first. If you add hydroxide concentration rises. Normally, without a buffer, that would lead to an increase in pH because you now have a higher hydroxide concentration, lower H3O plus concentration. But the buffer will resist that change and not allow the pH to change significantly. What happens instead? Of course, we shift to resist that change in accordance with LCP. We shift to the left, which decreases our hydroxide concentration by reacting with acetate, increasing water, increasing acetate. Sorry, by reacting with acetic acid. I think I said acetate. Okay, and once again, once you re-establish equilibrium, what you'll note is the net pH change here, or the net hydroxide change, is virtually negligible, or very, very small. Yes, you do have a slight increase in hydroxide overall. Yes, you 100% do, but it's very small. And so the pH hasn't changed significantly. No, it's an insignificant pH change because it has been resisted by the buffer. That's what we mean. And you can visualize the buffer as these 2 bars that get pushed up or down depending on how much acid or base is in solution. Then you can understand why we can buffer both in the acidic and basic direction until one of the sides is essentially fully consumed. Is that okay for everyone? Any questions? Have I missed any questions? So past equivalence point, the buffer is gone, and it has gone past capacity. Yes, Jared, that's correct. And I'll touch on that again in just a sec. So pH remain relatively the same. Yes, that's what we said. Cool. Any questions, pop them in chat, but I'll keep on going. Okay. So let's have a look at some questions in order to apply what we've said. Have a go at this one here. A, B, C, or D. Which of the following will be the most effective buffer solution? A, B, C, or D? What do we think? Type in chat. And if you're extra good, justify why. A, B, C, or D. Which of the following is the most effective buffer solution? There's 30 or so of you in here, so at least a few more responses. We've got a few active people, which is great. But if you haven't responded to anything yet, take this as your chance. Jump in now. Give it a go. It's okay if you get it wrong. We're all here to learn. What do we think? Callista's in with B. They're equimolar and high concentrations. Sounds pretty intelligent to me. Jared concurs. So does Archid. So does PRSPP. 4 Bs. And yes, Liana says as well, B. It is in fact B. So when we talk about effective buffer solutions, we want to have equimolar parts, which means effective buffer capacity in both directions. And because we simply have the highest concentration for both of these solutions, we'll have the greatest buffer capacity. I think it's not really too much of a contest between the others. They're all 0.1. This is clear cut going to be the greatest capacity. And yes, of course, we can also rule out D. I sort of skim past it, but D doesn't make sense because this is a strong acid and its conjugate base, which would not form a buffer. All right, cool. This is in the wrong place. Let's get rid of some of these. All right. So with this final development here, explain why this solution forms a buffer and calculate the pH of this buffer solution. What I'll do instead is I'll give you a model response for a buffer explanation, instead of doing this question, but I'll also give you this question anyway. So feel free to take a screenshot or come back to this, have a go at this. The first part is just explaining why it's a buffer, quite straightforward, 1 mark. Second part is a buffer calculation. And a lot of people haven't seen buffer calculations until it's too late, but it asks to calculate the pH of a buffer solution formed from 100 mils of 0.1 molar HCN or 0.1 molar NaCN. Once you've seen it, it's straightforward, but if you haven't seen it, have a go at it, and I'll scroll down to the answer as well. Take a screenshot if you haven't done a question like this before. Take a screenshot if you haven't done one like this before. Have a go at it in your own time. We won't go through it all today, just to make sure we get through everything. Okay. Cool. And then I'll take us through a model buffer response. Okay. So here, let's talk about part A. Again, part B is a buffer calc, but we won't do it. These are from the Catalyst notes, mod 6, but part A is explain how ethanoic buffers work to resist pH change, use equations to answer. Typically a 3-mark or maybe even 4-mark response, and the things you need are pretty much predefined every time you see this type of question. You have to talk about your equations, or you have to have them. You need to talk about what a buffer actually is. So oftentimes the first thing you'll do is actually define your buffer. And finally, you talk about how the resistance occurs for 1 or 2 marks. Resistance explanation. So what does that look like? That looks like this. So your 2 equations are your weak acid and its conjugate base reacted with water to show the ability to form hydronium or hydroxide. Your definition, as we've already talked about today, goes on here. Each of these could be worth 1 mark. And then the 3rd mark is attributed to the explanation of what happens when either hydronium or hydroxide is added. Typically, a question that's worth 4 marks can demand you to do both ways, but more often than not in your exams you get defined one of the ways. So they will ask what happens when you add an acid in and explain why pH doesn't change. Question, how many equations will be required in this type of question, 3 or 4? 2 is safer. You can get away with 1, but I would do 2. I think we've got some chemistry friends in the chat, which is nice. Okay. So with the explanation itself, this wording is solid. When H plus is introduced, system shifts to negate the change, as equation 1 shifts to the left, in accordance with LCP, which states a disturbance to a dynamic equilibrium resisted to counteract change. First time you mention LCP in exam, you have to define it, and if you're not sure or you just want to play it safe, define it every time it's mentioned for the first time in a question. For a mod 6 exam, I don't imagine it'd be too many times, but I would always play it safe. The game of HSC Chem with exams is essentially making sure that every response can't possibly lose marks, and you have to balance that with time. That's the exam strategy that you're playing. The second part is then the H plus reacts with existing ethanoic to produce ethanoic acid, shifting equilibrium to the left and reducing the acidic pH change. And you can add on if you want extra detail as concentration of H2O plus does not change significantly. As we said, using the arrows, if H2O plus goes up, the resistance is going to be pretty much the whole way back. And so the net change is very small. Okay. Any questions there? Buffers. Are we happy to move on to back titration? Questions? Anything at all? Can be the smallest question. Happy to answer anything. Okay. Cool. If no questions, let's move on. Oh, would we have real life example questions? Yeah. Yes, you would. Correct. So those real life examples, what I would recommend is to take into your exam at least one case. That way, if you're asked for an example of a buffer and to explain how there's one natural system or there's one natural buffer, explain how it works, you can at least talk on one example yourself without needing to be prompted. But the skill that's more necessary and relevant now is being able to look at a buffer for the first time, a new natural system they bring in, and explain how that's working without having seen it before and applying your understanding. That's the direction the HSC moves. That's the direction a lot of trial papers are moving now, which is great. I think it's better. But you should take one in anyway. So here's the ocean buffer. I'll leave that up for a second. Next question. So equilibrium shifts to the side where the added hydrogens or hydroxide are not on. Is it due to the increased concentration of hydrogen or hydroxide? Yes, correct. Because, again, let's have a look at this one. Let's say that into the ocean, the bicarbonate-carbonate buffer, as you add carbon dioxide, that produces carbonic acid, which produces hydronium and acidifies the ocean. So the bicarbonate can buffer that because as you add hydronium, that change will be resisted by shifting this equation to the left to make more bicarbonate and minimize the hydronium that's present. Hence the net change is relatively small. So it's always shifting away from the hydronium or hydroxide if you talk about the same ion in the same equation. The only case where that doesn't apply is if you're explaining through the top equation, let's say you're using the top equation number 1, and you're explaining how hydroxide changes are buffered through that equation. How would that be different? If you're adding hydroxide, the hydroxide would instead react with the hydronium, which means you now have less hydronium, and this equation would now shift to the right to replace the hydronium and consume some bicarbonate. So it depends on which equation you're using to explain which either acidic or basic change. Hope that makes sense. Rosaline asks, beside blood, how can we be asked in regards to other real life situation? So there's blood, obviously, as you said. You can also be asked on, let's say, this ocean buffer. Let's say that your school taught you about the blood buffer. They hadn't showed you the ocean one before, and they pull up the ocean bicarbonate buffer in your exam. And they say, explain how this bicarbonate-carbonate situation buffers a pH change in the ocean. How does it combat carbon dioxide being added into the ocean and acidifying it? And you should be expected to look at that system, recognize it's a buffer, and then talk about and explain the buffer as you do in any other case. Ethan asks, yeah, because LCP, oh no, it's not a question. Yeah, because LCP counteracts a change by using up the added something. Yes, correct. Answering Calissa's question, and you're correct, Ethan. Thank you very much. Okay, I'm going to take it. There's no more questions here. Let's move on past buffers, and let's now talk about our back titration. Okay. Can I get an indication in the chat? How do we feel on a scale of 1 to 5 in terms of our confidence for back titration? 1 being really bad and 5 being on top of it all over it. 1 to 5. Where are we all at with it? 3. Joel asks, isn't there a level H3O addition where the buffer capacity? Yes, correct, Joel. So, actually that's a fair point. I sort of didn't talk about the last part. Once you neutralize all of your buffer, and you reach buffer capacity, any additional, let's say you're adding H3O+, you're adding acid, once you exhaust your buffer, any extra H3O+ being added can't be buffered, and so that will just push your pH down and down and down, as your H+ concentration cannot be resisted anymore. Does that make sense? Let me know if it doesn't. Okay, so for back titration, it looks like we're sort of 3s. We've got some 0s, which is scary. Let's talk about it. I've got a 4 and a 2. Okay, great job. All right, so you all know titration, I'm assuming. You've all done a titration, you're all masters at it. But there is a extra type of titration in Mod 6 that if you don't know and you've not seen it by the time it comes in your exam, you will score 0 or very close to it because you just won't know what to do. And this is back titration. And as I said, this is targeted towards the band 6 level, getting 90% plus. If you're just aiming for a band 5 or a band 4, probably don't direct your energy here. It's not worth the energy. But if you're going up for that band 6, definitely this is where you want to put your energy. And before we go on to this is the point where I'll share the free gift for you guys. Let me just get the link together. Drum roll, please, as to what it is. I'll announce it in just a sec. Okay, got the link here. So link to get the gift is in the chat now. It's a little form. Just fill out the form with a few details and you'll get the link to the gift. The gift is from our Catalyst question compendium. So our Catalyst question compendium is for our students. We've essentially compiled questions from past trials, split by syllabus dot points. It's about 200 pages for mod 6-ish, 200-ish. And we've taken out all of the titration questions for you guys with the answers and put them together on the gift. So you guys can get that completely for free. Just go through that form and it'll be behind it on the thank you page. But yes, lots of titration questions for you to work through, so you don't have to scour through papers and look for them in your own time. Save the time. Just look through this doc and get a really good idea of what is needed from you in terms of titration calculations, titration explanations, those types of questions. There's 66 pages of questions, so I think you guys will be busy. All right, cool. One more question on buffers before we start back titration properly. Exam for mod 6 is only on buffers. Rough. We will have to critique a student's method towards something with buffers, making them comparing ratios or effect. Yeah, I mean, that makes sense. I'd imagine it's going to be a prac where you, as you say, make a buffer. And I think a likely prac, at least the one we have in our notes, is the one where you make buffers with different, or you try to make buffers with strong acid and its conjugate versus weak acid and its conjugate. And you can compare how well pH changes resisted across different combinations and basically figure out what a buffer can, when a buffer can or can't form, and also how much acid or base a buffer can resist. So you're testing different amounts being added in and what the pH change would be. And you'd see for a buffer, there wouldn't be much pH change, or where there isn't a buffer, the pH change would be very drastic off just a small change. I think that's quite likely. Question, does the link have buffer and titration or all of mod 6? The free resource is all of titration. So all the titration questions compiled together. Not as much on buffers, but definitely back titration, definitely titration. The full compendium is reserved for Catalyst students, unfortunately. But if you do want it, you can join for next term and get all of it free the moment you join. So up to you guys. But the free one is all the titration stuff. Okay. Cool. So back titration. What is it? Can anyone try to summarize it in their own words? Same exercise for buffer again. Test yourself. What does it mean when we say back titration? What's the method? What's involved? When do we use it? What are some thoughts around that? And any thoughts here are good. Doesn't really matter, doesn't be complete. Just pitch in ideas. As always, I'll give you a bit of time. I think some of you are typing probably. What is back titration? What does it entail? We're stunned into silence. Nice. Okay, Jared's in. Titrate the excess substance to calculate moles. Great. That's the end portion of a back titration. Perfect. Use when a reaction is gaseous or weak to find reactant concentration. Very good. Anonymous user. Yes. So when you have a specific reaction that can't be guaranteed to go to completion without a complete reaction, a back titration can be helpful to ensure you go to the full point of neutralization. Okay, cool. So essentially a back titration is performed firstly in cases where direct titration is hard to do. This is where you may have neutralization that is only partial or can't be guaranteed to go to completion. So for example, in the case of aspirin, which is where this comes up nice in the syllabus, in the case of an aspirin tablet which has acetyl salicylic acid in it, it's not very highly soluble. So when you dissolve it in solution, some of it may actually not fully dissolve, and it doesn't react very quickly. In fact, it reacts quite slowly. So if you were to do a titration on aspirin, you have to wait for the full reaction to occur, and oftentimes that's not practical because it's just going to create inaccuracy when you're getting to the equivalence point going dropwise. So a better way of doing it is taking your aspirin, putting it in solution. So you have, let's say, really nice number. Let's just say you have 1 mole of aspirin in solution. There's a lot of aspirin, but 1 mole of acetyl salicylic acid, or ASA, just going to simplify it down. You have 1 mole of ASA. A really simple way of doing it instead is you add a known, do it in blue, a known amount of base. And not just a known amount, but a known amount of base in excess. So what that means is you add, let's say, 2 moles of base, and let's just simplify it down. Base it being hydroxide moles, and acetyl salicylic acid being moles of neutralizable H+. Of course, at this point, we don't know how much H+ is in solution. But what will be left behind from that is we'll have 1 mole of base that goes unreacted. Since the 1 mole of H+ reacts with 1 mole of OH-, and 2 minus 1 is 1. So we have 1 mole of leftover unreacted base. We can then perform a second titration, sorry, not a second titration, we can now perform a titration on this excess amount of base using, again, a known acid, which will tell us we have 1 mole of base in this solution, or the correct concentration, which can be used to go back, hence back titration, working back to the first step, to tell us how much H+ there was in the first place, by saying the total base is equal to the unreacted plus the reacted. Actually, I'm going to change the numbers to make it simpler, because 2 and 1 is a bit annoying. Let's change it to 3 moles, and then you would have 2 moles left over. That should be a bit clearer. 3 moles and 2 moles left over, because 1 mole reacted with the H+. So you can then work back, because you can say that the total base we knew was 3 moles. The unreacted base, which we found from our titration, was 2 moles. And therefore, the reacted base has to be 1 mole, which is what we're trying to find. And that 1 mole reacted with 1 mole of H+, which tells you how much H+ was in that solution, which has been completely reacted. So that's the overview of back titration at a sort of just bird's eye view in. What you need to then be able to do with back titration is you need to be able to perform calculations such as this one here. I think this one's really nice because it's quite simple. It's a really old HSC question. I'll give you all a chance to read this and we'll have a go. Question in the chat, do we need to know this acid? You do not strictly need to know, I mean, obviously it helps, but if you're just trying to find the H+ content in solution, and you know the proticity of the acid, you can do it that way, but knowing the acid will obviously help. It would help with the stoichiometry in particular. Is this video going to stay recorded and uploaded on this page after it ends? Yes, it will. So if you do have to head off and you've got other things to do, other study to complete, feel free. But this will go back up. It just may not be in the next 24 hours. YouTube can sometimes take some time to process. Okay. Before we go into the calculation, I'll explain it one more time through a different way to visualize, and then we'll go into the calculation and let you all have a go. So in your back titration, starting again, you have an unknown amount of acid being analyzed, and that's dissolved into solution. We'll go for about another 10 minutes or so. You have an unknown amount of acid being analyzed, it's in solution. You add an excess amount of base, all of this, that is known, and a portion of it gets reacted with the acid that was in solution. That leaves behind an unreacted part of base, which you then take and you titrate in a titration. The titration perfectly neutralizes the remaining base with a known acid, allowing you to find the moles of base in excess. So you know the excess base, you know the original total base, because you know the initial volume and concentration of base you added in, which means you can find the reacted by subtracting them away. And hence your back titration is complete, because you can use this reacted portion to find how much acid was reacted total. Hopefully that makes some sense. And if it doesn't, because I still think it's quite abstract without having done some examples, let's have a go at this together. So back titration worked example 2009, reading through. The nitrogen content of bread was determined using the following procedure. Sample of bread weighs 2.8 grams. Nitrogen in the sample was converted into ammonia. The ammonia was collected in 50 mils of 0.125 molar hydrochloric acid, and all of it was neutralized, leaving an excess of hydrochloric acid. The excess hydrochloric acid was titrated with 23.3 mils of 0.116 molar hydroxide solution. First of all, write a balanced equation for the two reactions involving hydrochloric acid. So start working through these. I'll write up my answers as we go along. So balanced equations for the two reactions involving hydrochloric acid. Have a go. Don't forget states. Okay, cool. So the two equations are up. You have your HCl reacting with NaOH to make H2O and NaCl. NH3 also reacting with HCl and to form ammonium chloride, as per earlier in the question. So 2 marks there. Part B, calculate the excess moles of hydrochloric acid. The start of any back titration starts from the very end. So to find the excess hydrochloric acid, you need to find how much sodium hydroxide was needed to neutralize it, since they neutralize in a 1:1 ratio. Have a go. Starting with the moles of NaOH is equal to C times V, which is 0.116 times Y at 0.0233. And that number cool. 2.70 times 10 to the negative 3. Best practice is to save your numbers as you go along. So the save function in your calculator, I don't know if the new calculator is the same, but mine's shift store, and then you choose a letter. So I save it as A, shift plus store plus A. Okay. You know this is the moles of NaOH, which is equal to the moles of HCl excess, since that's what you titrated in the second part of the titration, or the second part of the question. Okay. Part C, calculate the moles of ammonia. All right. The next thing we can do is we can go back and find what the total amount of HCl is, because as we said, total is equal to unreacted plus reacted, and therefore how much ammonia, or how much HCl reacted rather, would be equal to the total minus the unreacted. We already know this amount is the unreacted because it's the excess, so we need to find the total. The moles of HCl total is equal to 0.05 liters times by 0.125 molar. And that gives 6.25 times 10 to the negative 3 moles. Therefore, reacted HCl moles is equal to 6.25 minus 2.70 times 10 to the negative 3, which is equal to 3.55 times 10 to the negative 3 mole. 3.55 times 10 to the negative 3 mole. And as we said, because the reacted HCl reacts in a, we're back up at part A, the NH3 reacts with HCl in a 1-to-1 ratio, 1 to 1. This number is equal to the moles of NH3, since it's a 1-to-1 ratio. Okay, any questions, put them in the chat. We're almost there. We've worked all the way back to find how much ammonia there is from the back of the back titration to the front. The final thing to do is calculate the percentage by mass of nitrogen in the bread, being very careful of nitrogen, not ammonia. So, if we know the moles of ammonia, the moles of NH3 is equal to the moles of just nitrogen atoms, since in every one ammonia there's one nitrogen. Then you can say therefore that is equal to 3.55 times 10 to the negative 3 moles. And the last thing to do is to find the mass of nitrogen, which you can find by 3.55 times 10 to the negative 3 times by 14.01, nitrogen's molar mass. And that ends up being times 10 to the negative 3 times 14.01 ends up being 0.0497 grams. And because we had 2.8 grams total, we can now find what percentage of nitrogen existed in the 2.8 gram of bread. So the percentage nitrogen by mass is equal to 0.0497 divided by the total mass 2.8, which gives, and we can do times 100% to give it in percentage, equals 1.78% to 3 significant figures. And with all calculations, ensure your sig figs are right by checking your question stem and looking at what's the least number of sig figs. We have 3, 3, 3, 4, and 3. So the least sig figs is 3, hence we leave our answers to 3 sig figs, as we do in part B, in part C, and then now part D, to 3 sig figs. Okay. Any questions there on the back titration? Any questions? Okay. Cool. If no questions, then that's back titration. I'll give you one more question to work through for the road. Back titration question 3. Take a screenshot. Yes, Tommy, I can go back in just a sec. back titration 3, take a screenshot. This one's also on the moderate side, not too bad. Take a screenshot, and the work solution is here for you to reference later once you've had a go. All right, cool. Jumping back for you, Tommy. The last part, starting from the question again, calculate the percentage by mass of nitrogen in the bread. First thing is to find out from the information you had. You know how much ammonia was in the bread that was formed. And because all of the ammonia, or all of the nitrogen in the sample is turned into ammonia, we can assume that since ammonia has one nitrogen per molecule, that all of the nitrogen is now in ammonia form. And to go back to how much nitrogen we have, it's a 1-to-1 conversion. We just say that the moles of nitrogen is the same moles of ammonia. And so that's the first thing we do. The moles of nitrogen is the same as the moles of ammonia, 3.55 times 10 to the negative 3. Then, because we're trying to find the total nitrogen content in the bread in mass, we multiply it by its molar mass of 14.01. And that gives us the mass. Question from Jared, why isn't it N2? It could be N2, but it doesn't really matter for us, because whether it is N2 or N, we know that the total number of nitrogen atoms is this number. And if it was N2, sure, you would have the moles of N2 is equal to 3.55 times 10 to the negative 3 on 2. But then you just end up getting the same number of moles of nitrogen once you multiply by 2 to get to the nitrogen moles. Or if you kept it as N2 and then multiplied it by the molar mass of nitrogen molecules, it'd be the same number anyway. It's a good question, but it doesn't affect it in this case. And no worries at all. Hopefully it has helped. So we've got to our final step. We know the mass of nitrogen, and the final part is finding the percent by mass in the bread. We know the total mass of the bread is 2.8. The mass of nitrogen content is 0.0497 grams. And so to find the percentage, we just take how much is nitrogen divided by the total mass, which gives us the percentage of the total mass that is nitrogen. And that's 1.78% to 3 sig figs. Okay, sweet. Cool. So that's all on back titration. The last thing I'm going to give you guys before we finish up today, and I'll put in chat again the gift in case you missed that from before. The final thing is I want to give you a list of calculation types to go revisit if you haven't already gone back and checked, all the calculations in this module. So the list of calculations you should know. If you don't, have a look. Let's open up a blank page. Mod 6 calculation checklist. Number 1 is your basic pH calculations. So obviously being able to turn H plus concentration and OH minus concentration into pH. I don't think any of you would have problems with this, or pOH. Then you have your pH of weak acids and bases using Ka/Kb. Really common question type. You have your pH of strong acid, strong base in solution. You don't need Ka and Kb because you can just assume full ionization. You then have pH after neutralization, which is essentially a limiting reagent question. Limiting reagent, which then flows into one of these two, depending on whether your excess is strong or weak. So pH after neutralization, very common. Very, very common. Then, as I said before, you have your pH in buffers. So your buffer calculations, have a look back at the example if you haven't done these before. So when you form a buffer, what will the pH be? and you're essentially doing a ice table and small change assumption to solve these using a Ka/Kb. And those are the main pH calculations. Each of those archetypes, extraordinarily common, know them well. Then there's a whole category of Ka, Kb, pKa, pKb questions, and also Kw. So each of these arrows indicates how you can convert between each of these terms. So you should be able to convert Ka to Kb. You should be able to turn a Kb into a pKb, or you should be able to turn a Ka and Kb into a Kw, and all of this. So this little, I guess, pentagon shows you all the ways you can convert between these terms, and you should be able to form these expressions, be able to find pK, find pKb, so on. Then you have neutralization enthalpy. Questions where you're essentially using Q equals mc delta T, and you're using delta H equals negative Q on N to find out temperature changes in neutralization, to find out heat capacity constants, to find out what the enthalpy of neutralization is. Keeping in mind what the difference between this N and this M is, most common mistake there, and also your units on C. Catalyst students should be all over this, it's all through the notes. Then we have, of course, the final part of the module, which is your titration calculations, so finding concentrations. Won't speak too much on that. And as we talked about today, your back titration, which is the extension of titration. Within titration, you obviously have your pH-based, you have your conductometric, so you need to know both of those. And if you're unlucky and your school wants to go ahead, you might also get precipitation titration this term, although this is more of a mod 8 concept. Okay, and so that's all of the mod 6 calculations you need. If you haven't seen these, hopefully you do see them before your exam, just so you're prepared. These are all through the Catalyst compendium for the Catalyst students here, also through the homework, also through the notes. So you should have covered all of these if you're a Catalyst student. And just going back to some questions in the chat, could you quickly explain why all neutralization reaction be forward? Why all neutralization reaction be forward and between NH3? I'm not sure I quite understand your question, Joel. But yes, you wouldn't form water from a neutralization with NH3 because it doesn't have oxygen, as Ethan says. That is true. And because it's a Bronsted-Lowry neutralization, where you simply have a donation of a proton. So you're donating a proton from the acid to the NH3 to make ammonium instead of a water molecule. User asks, how are ice tables related to pH? They're related to buffer calculations because it's the only way to solve them. Otherwise, you have to solve a quadratic, and NESA doesn't require quadratics for chemistry, which is nice. Are static equilibrium reactions the same as non-equilibrium reactions? Yeah, I think of them that way, where they're going to completion. So yes, I'd say so. Weak acid loop, there is still no equilibrium, but rather a solid arrow. Oh, okay, I see what you mean. Gotcha, cool. So, to answer that question, why in a weak acid, weak base neutralization do we go to completion, essentially? So if you reacted acetate or acetic acid with NH3, why does this go to completion and not just, why is it not a double-ended arrow? It's a good question. It's a very important one to understand conceptually. Okay. Q, 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 A, Q. Okay. So, For our acetic acid, we know that it makes CH3COO minus plus H3O plus if left to its own devices. Same for NH3, we know it will make NH4 plus and OH minus, again, if it's left to its own devices and it reacts with water. So, essentially what happens here is because you may only have 10% of your acetic acid dissociated and 10% of your ammonia in the hydroxide form. So let's say we have 10% of the concentration in this form, and same here, 10% in this form, and we have 90% in the undissociated or unneutralized forms. What happens here is that the formed and free hydronium and hydroxide will react to make H2O immediately. So it will just react to completion because we know that is a one-way reaction, that neutralization. And so what is that doing to these two equilibria? Because this, in truth, these are both equilibria. The dissociation of the ionization of acetic acid and the ionization of ammonia. If you react all of the free hydroxide, so now you have essentially no hydroxide, you have no hydronium, what's going to happen to this equilibrium? Which way will it shift? It's going to, of course, shift to make more hydronium and to make more hydroxide. So now, your system is going to shift towards making more of these. You're now consuming down to like 81%, and this is now down to like 9%, assuming the total is 100%. Now this is like, it's all funneling down into water. But now that you've formed more H3O plus and you form more OH minus, the same thing happens again. This 9% reacts with this 9%. These react and form water. And so the whole thing happens again. You shift. Now we've consumed more of our weak unionized acetic acid. Now you have, let's say we've done this a few times. We're now down to like essentially zero, or you'd eventually get to 0%. Because the same process happens. Every time you ionize more H3O plus and OH minus, that reacts, shift, more H3O plus and more OH minus, reacts, shift, and eventually you get to a point where you've reacted all of one of these weak acid or weak base, and you've got a limiting reagent in play. And that's why even for a weak acid, weak base neutralization, you're going to go to completion. And it's a single-ended arrow, not a double-ended. Does that make sense, Joel? I know it's a bit long-winded, but you have to sort of understand the progression through each of the neutralizations that we're shifting, and we're shifting, and we're shifting until all of it's reacted. Okay, sweet. Awesome. Cool. So that's pretty much all for today. I know we're only going to go for about an hour. We've gone a little bit longer. So if this was helpful, let us know on Instagram. Send us a DM. Let us know it was, because then if we know it's helpful for you guys, we'll run more. Just a final thing from me. As I said at the start, we are open for enrollments for term 2. And if you found this helpful, submit an inquiry form, see if it's for you. And when you do enroll, you get access to all of the mod 6 from this term, free. You get all the resources, all the questions, all of the, literally everything, exams, support, everything, when you sign up for the next term. Plus, if you're signing up before March 29th, you get that little discount for being an early bird. Okay, if there's any more questions, chuck them in the chat, and I'll go through them to finish off today. But otherwise, thank you very much for everyone who has tuned in today. It has been an absolute pleasure taking you guys through some of these trickier, hairier concepts from Mod 6. And I'll post in chat one more time the gift in case you've missed it. But we do have one question in the chat. So there is a solution where water is solvent with acetate ions and ammonium in solution. Yes, that is true. There'll be a solution where you have acetate ammonium formed from the complete neutralization of one of the acid or base, and you will have an excess of one of the acid or base. So you might have an excess of ammonia, for example, and you'd have a little bit of this, a little bit of this, a little bit of this. I think that's the simple way to put it. You will obviously have some acetic acid form back from the equilibrium of having a lot of acetate there. So it is a bit more complicated, but for our sake, a weak acid will neutralize the completion even if it is a weak acid, if that makes sense. As long as there's ample moles of the opposite acid or base, respectively. So if it's a weak acid and there's lots of base in solution, the weak acid will completely neutralize even if it doesn't dissociate fully on its own. And it's because of this constant shifting. Okay, cool. I've got no more questions in the chat. So for those of you who are still here, thank you very much. Appreciate the time you've put in tonight. Hopefully it was helpful. Again, enrollments are open on our website. Do let us know and we'll give you a call if you're interested. Otherwise, enjoy the rest of your Tuesday. Enjoy the rest of your week. Best of luck for your exams, those who have them on tomorrow, the day after, next week, whenever they are. Best of luck. We'll see you in the next stream, or we'll see you inside Catalyst if you guys are keen for that. But otherwise, best of luck. See ya.